Recording. So, last time I introduced you to this thing called the operational amplifier, right? So there's these little spider-looking things with 8 little legs, right? And the way you tell which orientation it is that either the notch or the little dot tells you which way is up, right? Okay. And you're gonna see that when you do the lab on this next week. Okay. We went through, how the operational amplifier works. Does anyone remember how do we figure out, how do we determine what's the behavior of our operation amplifier if we put it in the circuit? What are the rules that we should follow? Right, inputs. Impedance is basically infinity, or that the current, right, into the input, right, either A or B, right, or plus or minus, right, usually it's either, come on, let me erase. You can do it, computer. I think there was an update over the weekend, that's why my computer is slow now. Right? Either that, right? You can either think about the input impedance being infinity, or that the inputs don't draw currents at all. Okay? Anyone else for rule number 2? Right. Well, it'll try to make it so that the plus and minus input, or more accurately, the inverting and non-inverting inputs have the same voltage. Okay? And it's going to behave that way in order for you to have this thing called the feedback loop. The idea is that you're looking at the output and then putting it back at the input in order to have feedback. Just like if you're driving and you start veering to the left, right, you correct by steering to the right to go back to the center of the lane, right, so you don't crash into people. Okay. So what I'm going to do is we went through like the inverting amplifier, and in your homework you're going to do the non-inverting amplifier. I also derived a differential amplifier for you guys last time. That took like 15-20 minutes. I'm going to show you guys how this known as the adder circuit works. Okay, so this thing allows you to add voltages with different factors so that you can actually combine signals together. And typically this is used as what's known as a digital to analog converter. Okay, we haven't talked about what digital means yet, so that's why the book doesn't call it the digital analog converter, but this is basically what that is. But they call it an adder circuit right here. Okay, so one thing we could do is to analyze the circuit is just a lot of times what we want to do is just kind of assume some numbers here, right, and then see what the behavior of the circuit is, right? So whatever, let's say V1 is the only one that's not 0. Let's just make V2 and V3 0, right? Essentially what the circuit you have here is V1, right, going through a resistor 1, right, and that's going into the inverting input, and then the non-inverting input is tied to 0, and then you have a feedback resistor, right, and that goes to the output. Okay, what type of circuit is this? Well, if I want to write V out as a function of V in, what would it be? You guys remember that? V in as in V1. Yes, an inverting amplifier is going to be RF over R1. This is exactly what it derived on Wednesday last time. Okay, so right, that's if V1 is the only input that's not 0, right? Well, now I'm going to change the rule on you again, right? Okay, if V1 is 0, V3 is 0, V2 is the only non-zero, right? What will be the output instead? The same, but what's the difference? R2, V2, right? So the same argument can be made for V3, right? Okay. So these are just 3 separate inverting amplifier that will give you an amplification, right, with this ratio, RF over R1, or RF over R2 or RF over R3, right? That depends on for each of the voltage. So it'll amplify each of the voltage differently for you. Okay, so that's kind of nice, right? So what this is typically used for is a digital to analog converter. Okay, so what they would do, well, RF is a fixed number, so let's make RF equal to 8 kilo ohm. Okay, I'm gonna make R1 equal to 8 kilo ohm, R2 4 kilo ohm, okay, and R1 2 kilo ohm. Okay, that means the gain for V1, right, is going to be -1, right? Right. So that makes sense. Let's write this on a separate line. Let's not try to do too many equal signs, right? Gain on voltage 1 is equal to -1. What's the gain on voltage 2 going to be? What's RF over R2 now? Right, -2, yeah. Yeah, 2, or the gain is -2. Okay. And then similarly for V3, right, that's going to have a gain of 4. Okay. Those of you who are computer science, current or previously, will start to recognize these three numbers, right? So this is the binary first, the ones place, binary for the twos place, and this is binary for the fours place, right? So if this represent, you know, a number, if both voltages are high, right, this will be 1 plus 2 plus 4, which will equal to 7, right? Okay, but if, let's say, V3 is equal to 0, right, this number becomes 0 because, you know, no matter how much you amplify 0, you still get 0, right? So then you get a number 3, right? But if V2 is 0, then you get 1 instead, right? So this is basically a way to convert, right, a bunch of, go over here, right, digital ones and zeros, right, convert this to an analog number between 0 and 7, right? Okay, that's what this 3 input gives you. Okay, so this is a 3-bit analog digital converter. Okay, we're gonna see this again when we jump into digital logic in like 4 weeks, I think. Right? Okay, if you don't understand the binary number stuff, don't worry about it right now. It's not, you know, that's why they call it an adder circuit, right? Because it basically, what it does is it takes whatever the input of 1, right, add to it, input of 2, add to it, but with a factor of 2, take the input of 3, but add to it with a factor of 4, right? So what the resultant thing is, you're going to get whatever the input is, all negative, whatever input of 1 is, times a gain of 1, right, plus whatever input 2 is, times a gain of 2, plus a gain, whatever input 3 is, times a gain of 4, right? All of that gets negated because of the inverting amplifier part, right? So it adds V1, V2, V3 together for you, but with a coefficient that you can determine by changing what RF and R1 and R2 and R3 are. So I know this, you know, may not make a lot of sense on why it's useful, but that's why I try to bring in the digital to analog converter. But since you don't know what those are yet, then, you know, then it's not very helpful. But you'll see in a couple of weeks. So we're not going to build this circuit for like 2-3 weeks. Okay, so with that, we kind of finish up kind of like the first order application of operational amplifiers. Before I talk about active filters, meaning you can actually do amplification and filter with frequency, either like a low pass, high pass, or a band pass filter, the stuff you guys already know how to make, right? The book actually kind of covers, and I think this is useful, kind of covers, you know, what are the limitations on operational amplifiers? How much can you push these devices for them to work for you, okay? Okay. So the first thing we need to kind of note is that your operational amplifier has this thing called a voltage gain. Okay. Okay. This is something that's not the same thing as the circuit's gain, right? This has some gain, right? We calculate what that is, right? The voltage gain inside an operational amplifier is denoted by this symbol A naught. Okay. And so what the heck does A naught means? So the best way to look at it is to think about it in terms of a plot of the voltage gain, which is exactly what we just tried to introduce, is how big whatever your input difference is, how big can it amplify it? Okay, it's basically how big inside the operation amplifier it can amplify the voltages. Okay, not outside. So this is just a little bit of a detail about the internal workings of your operation amplifier. And this actually depends on how fast, right, you're trying to switch, right, the 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 operational amplifier as a function of its frequency. So for example, right, if I have some sort of sine wave, right, up and down, up and down, up and down like this, and I want it to amplify this signal, right, by a factor of 10, right, let's say up here, right, I know this misaligned, but just pretend they're in line, right, okay, so that's a, right, a voltage gain, oops, A naught, this is a voltage gain of times 10 at a frequency, let's say this wave is at, 1 megahertz, 1 million times per second, okay? So that's a gain of 10 at 1 megahertz, okay? So you can see this plot here, and this is for a particular operational amplifier. I think the ones we'll use is going to be closer to this A1, A01, where if you go too high in frequency, the gain basically drops, okay? The reason for that is that as the operation operational amplifier compares the two input, it cannot keep up how fast it can change, okay? Because every time you put in a 1 millivolt difference, right, the operation amplifier is going to try to make it like a million volts difference, right? Okay, so this gain here, right, it starts off, if you were at 1 hertz for this particular amplifier, right, had 10 to the 5, that's 100,000, right? Right, but as you increase how fast you're changing the signal, so how fast the signal is, let's say you're doing it at 1 kilohertz, now your gain is actually only 1,000. So you're a factor of 100 less of your maximum gain, okay? And most of the time it doesn't matter because like a lot of the amplifiers you're building, right, you're gonna make like a gain of 10. Like a gain of 100 typically is not what you're gonna, that's probably as high as you want to do on an amplifier. If you want to do a gain of 1,000, what you want to do is actually do a gain of 30, then another gain of 33 or something like that, right? That way you do this multi-stage gain as opposed to trying to get, a factor of 1,000 amplification right out of the box, okay? And so this is a complicated thing to quantify, right? In order to figure out what the hell's going on with my amplifier, I have to, look at this plot all the time. So there's actually a easy number to think about, and I'm surprised the book doesn't cover it. I think it does a little bit, but kind of skips around it. This is known as the gain bandwidth product, okay? And that's why I think I linked the Wikipedia article about it, because a lot of times the book doesn't cover everything, okay? So if you have a voltage gain of 100, and you can do that at 1 kilohertz, right? What the gain bandwidth product is basically what it sounds like. You take the gain and you multiply the frequency to it, and then you get one number instead, okay? So if I take 100, multiply by 10,000, so this will be a gain of 100 times 100, 10,000 hertz, right? If I multiply this together, I get a gain bandwidth product, okay, this will be 1000, 1 million, right? Hertz, okay? Or in other words, 1 megahertz, okay? That's what we define as the gain bandwidth product, okay? That allows you to kind of quantify how good this amplifier is, right? It can give you either a gain of 1 at 1 megahertz, right, because you're multiplying these two numbers together, or a gain of 1 million at 1 hertz. Usually you're operating somewhere between the two, right? So if you want a gain of 10, right, you don't want to run this amplifier at more than how many hertz? If I want a gain of 10. No, a little bit more. I'm sorry? This is 10 to the, yeah, maybe scientific notation might be easier in this case, right? So this is 10 to the 6, right? Okay, that's my gain bandwidth product, okay? And now my signal, my voltage, you know, input, right, the frequency is about, oops, I want a gain, right, equals to 10, right? What's the fastest you can run this amplifier? What will be the frequency of the input that you want? 10 to the 5, right? Right, hertz, and that's 100 kilohertz, right? Okay, okay. So this is how you can, just by looking at one number on your operation amplifier, see if it's good enough for, you know, your application. So, right. So this device, sometimes not only does it amplify things, right, badly when you go to high frequencies, some of them are actually designed to also not behave very well at low frequency, okay? And this is why when you set your function generator to like 0.1 hertz, then it starts to kind of wiggles a little bit. It's not designed for that. So our function generators are, you know, really meant for like 100 hertz to maybe 100 kilohertz, okay? And so this is known as the bandwidth of the gain at maximum gain. Okay, so this is another way to quantify things, where this width here tells you at which point where it gets the maximum gain instead. Okay, so let's say this number on the left is 10 kilohertz. The number on the right is 1 megahertz. The bandwidth, usually people just call it the bandwidth, right, will be 990 kilohertz. Basically, people will just say 1 megahertz because it's close enough. Okay. Okay. So to calculate this gain bandwidth product, you just basically take the bandwidth, right, and multiply it by the gain itself. Okay. And for the LF411, the ones you guys are using, I think this is actually not true anymore. So I think when I looked this up, when I wrote this lecture, it was 4 megahertz. I think this could be 3 megahertz now. Okay. So that's the gain bandwidth product for the LF411. Okay. So once again, I'm going to ask you, right? If I want something that has a gain of 10, what will be the fastest signal I can use for this particular amplifier? Okay. So if I want the gain to be at least 10, right? What will be the maximum frequency that I want to use this operational amplifier with? Anyone wants to chime in and answer? 300 kilohertz, right? Because another way to think about this is that, well, if it's 1 megahertz, then it's 100, right? If it's 3 megahertz, then it's 300, right? Or 300 kilohertz. Does that make sense? Okay. So when you guys are going out, you know, let's say you guys are going out and buying op amps, this is basically the number you want to look at to figure out how fast this op amp is and whether or not it can amplify the signal at the speed that you need it at. Okay. I'm going to look up the bandwidth for for the LF411 real quick just to double check what this number is, because I think I wrote 4 there. I think they are downgraded to 3 now. bandwidth product. A lot of times they just say bandwidth. Supply current. Okay, yeah, 3. Yeah, there's actually 3 now. Okay, so cross this 4 out. Okay, the stuff you have, it can usually probably do a little bit more than 3. So, because the manufacturer usually makes it a little bit better than the minimum that they need to pass the spec, right? So, so that's what they will do. Okay, and you in lab 5, you actually measure this yourself. Okay. All right. The other thing that happens with your op amp is that there's going to be a delay between your input and your output. Okay. And the reason for that is that there's just going to be, due to the fact that inside here there's a bunch of little circuits, right? And it just takes a little bit of time for that signal to travel from the input to the output. Okay. And this is typically on the order of 100 picosecond. Okay. Okay. You may say, okay, 100 picosecond, who the hell cares, right? When you start doing fast electronics, okay, that's going to matter quite a bit, okay? Because 100 picosecond, right? If I convert that to frequency, right? Frequency is 1 over the period, right? 100 times 10 to the minus 12, that's what a picosecond is, right? That's actually 1 times 10 to the negative 10 seconds. I flip this upside down, is 10 to the 10 hertz, okay? Right? 10 to the 10 hertz, that's 10 gigahertz, right? Okay? Your phone already works at about 2.4 gigahertz, okay? This is one of the reasons why consumer electronics tend to stay below 10 gigahertz, because they don't want to pay additional things to design a chip that can, where the signal can travel from one side of the chip to the other in less than 100 picoseconds. So when you start designing things that are less consumer application, and you guys probably know what I'm talking about when I say that, then you would need timing that are faster than that. Okay, so typically 100 picosecond is a good enough time for our normal everyday use. Okay, all right. Remember rule number 1 was that the input impedance, right, is equal to infinity, right? That's not true. Anyone want to tell me why that's not true? Not just not ideal, but like, if you, how does your multimeter measure voltages? You guys remember that from first day? How does a voltmeter work? There's a little needle, right? Well, used to be a little needle. What's at the end of this needle? A little coil, right? That allows current to run through it. And around this coil, there's a magnet, right? North and the south, right? When you run current through it, it deflects the coil because of the magnetic force, right? So in order to measure voltage, you need current, right? Right? And rule number 2 is that, right, the op amp is going to try to make V plus equal to V minus, right? If it has no way to measure V plus and V minus, then it can never do that, right? So in reality, right, your op amp does draw some current at the input, okay? For the LF411, it's going to be about a picoamp, okay? Very small, but once again, if you're dealing with very fast electronics or very precise electronic, that's going to matter, okay? Another thing is the input range. Okay, each op amp is designed to have a particular input range. Okay, so for the LF411, you can never go above plus or minus 15 volts. Okay, so these are low, well, these are moderate voltage applications. Okay, so you could have these kind of things that goes up to 10 kilovolts, 100 kilovolts, right? Or you can have things, op amps that are designed to deal with things on a millivolt or a microvolt level, okay? So this is sort of like the cheap middle ground where it's easy to make, and when you guys burn a few of these, it's not a big deal to the department because each of them cost like $1, okay? Okay, so that's one of the things that when you want to look at operational amplifiers is that what is the input range that is designed for, okay? You don't want it to go up, too far. You don't want it to go above or below that, okay? Okay. Next thing is the slew rate. Slew rate. Slew rate is a kind of an interesting thing where, let's say, right, this dotted line, sorry, look at the solid line first. The solid line is actually what the output is supposed to be for your operational amplifier. Okay, the dotted line is actually what's happening in real life. Okay, as opposed to that voltage going from negative 10 volts to positive 10 volts instantly, that doesn't happen. Okay, it does take some time for the amount of charge to build up inside your transistor in order for that to happen. So this is known as a slew rate. The slew rate is basically, right, let's say if you're going from negative 10 to positive 10, oops, right, and the amount of time it takes for that to happen, right, unfortunately this is kind of small. I'm going to draw it here, okay? Delta T. Let's say the amount of time for that to happen is 20 microseconds, okay? The slew rate, it's usually symbolized by SR. This is 20 volts, right? From negative 10 to positive 10, you have a change in voltage of 20, right? Divided by 20 microseconds, okay? So the slew rate is actually 1 volt per microsecond, okay? So what you have up here is the delta V divided by delta T, right? Okay. And typically slew rate will be given in volts per microseconds because that's usually how fast they will be operating at, okay? If you have an op amp that has a spec that has volts per picosecond, that's a really good op amp, right? Because it can ramp 1 volt in a picosecond instead. Okay. Right. For the LF411, it can do 15 volts per microsecond, 15 volts every microsecond. Okay. So that's the op amps, and you're gonna see this when you're doing the lab. Okay. Input bias, input offset voltages. Okay. So remember, one of the things is that the operation amplifier, one of the golden rules I tell you is that it's going to make V plus and V minus always the same. Okay, there's going to be some uncertainty in that. Okay, so in the LF411, the voltage offset that could be possible between them is about 0.8 volts. I'm giving you a lot of just kind of information about our particular op amp. You're going to actually see this in the lab in a couple of weeks when you guys do this measurement yourself. Okay. Right? So, 0.8 millivolts, right? Difference between the inverting and non-inverting input, right? That's a very small difference, right? For what we're doing, right? We're doing things on the order of 1 to 10 volts, right? But if you're trying to measure something that's on the order of 1 millivolt, that's going to matter, right? So don't use this op amp if you're going to measure anything with 1 millivolts, okay? In fact, I can tell you now where I got this 4 megahertz number from. The gain bandwidth product that was there before, right? So this is not accurate anymore. So I got that number from the textbook. Okay, so Texas Instrument since then have updated their product information so that is actually not, the textbook is not as updated as what you see on the spec sheet from Texas Instrument. Okay. What I want to do now is kind of show you guys how to look at this information when you are trying to figure out what kind of op amps you need for your particular application. So I'm going to hop over to this computer. So unfortunately the recording is not going to happen on the screen. Okay. So whenever you have a particular operational amplifier or any type of electronics part, okay. Okay. Don't look at that. That's like $7,000. So if I want to figure out, okay, what is the specification for our op amps, right? So LF411, don't look at the history because I've already seen this many times. So what you want to do is look for what's called the data sheet, okay? So just type in the name of the device and data sheet, okay? And usually, so don't click on the advertisement from Google, but this is not an ad, right? So it says, right? Um, Usually the first one probably works, okay? Right? And it should bring up this white paper type of document for you, okay? And this tells you basically what is the input bias current, 50 picoamp, okay? So I think previously a book says 200 picoamp. So yeah, this is actually better now. Input noise current, so there's just some noise on the picoamp level. Um, Supply current, it's just drawing some current from your power supply. And then you have the pin out, right? So you have the VCC here, the non-inverting input here, the inverting input here, and then the output is over here, right? And then you can actually even balance the input and output by putting a little bit of voltage there to, if you want V in to be always bigger than, sorry, if you want V plus to be always bigger by 1 volt than V minus, you can actually do that with a balance, okay? It's just a way to tweak the um, the input so that you don't have to have exactly zero, you don't have to have zero there, okay? And you have a little symbol right here that shows you, what it looks like on a schematic sheet, right? And all of this, right, shows you what the specification. So the supply voltage can be up to 18 volts, right? Right. Typically, when you're running these things, you don't go up to the spec. You just go like, maybe 10% lower. So we're running these, I think, at 15 volts, plus or minus 15. Okay. Let's see. Short circuit. There's some power dissipation. So it dissipates about half a watt. So it would get warm, okay, as you use it. Okay. And let's see. Operational temperature. So these are not designed to go below freezing. Okay, don't put them in the freezer and expect them to work. Let's see, what else is there? So yeah, this input offset voltage, remember I just talked about that? The voltage is going to try to make it close to zero, but there's going to be a slight difference, and this difference is 0.8 millivolts, okay? Very small. That's what typical is. Maximum, meaning they will still ship the part if they measure this to be 2 millivolts, okay, and sell it to you. But their hope is that it's going to be around 0.8, okay? What else is a good? Oh, so like, yeah, the input bias current, right? Remember we said that in order for it to know what the voltage at the inputs are, right, it has to sample a little bit of the current, right? So that's 50 picoamp, or the maximum is 200, okay? So if you get a 200 picoamp one, then yeah, you just got a pretty shitty one. But most of the time it should be about 50, okay? Um, if you run these things at a higher temperature, right? So be careful here. This is a nanoamp, right? So if you run it hot, you're going to have a lot more input bias current. It's going to draw a lot more current as it gets hotter. Okay. I'm trying to get to the gain bandwidth thing. Where is it? Oh, there's the slew rate. Okay, down here, right? Typical is 13 volts per microseconds, right? I think I said 15 in the lecture, so now they're downgraded it to 13. Okay, so these spec sheet, the reason I look it up is because as the manufacturer, tweak their recipe for making these things, they're going to change slightly, okay? All right. Where's the gain bandwidth product? You guys see it? It should have units of hertz. So usually what I do is I just look up on the right-hand side, stuff that has the right units for me to look at and figure out what I need to find. There was hertz under the slew. Oh yeah, okay, so instead of calling it gain bandwidth product, they call it unity gain bandwidth. That means if you have a gain of 1, what is the bandwidth, right? But that's basically what the gain bandwidth product is. If you multiply 1 times the gain bandwidth product, you still get that same number. All right, so it's 3 megahertz, okay? So So you're going to be looking this stuff up in the homework, and that way you actually know what you're plugging into your breadboard. And I'm going to have you, I think in the homework, I also have you look up a faster one and just see, you know, what an extra 20 bucks buys you. Okay? All right. Any questions about that? About these little specification stuff? Oh, there's already over here. Okay, let's skip all this because I think I'm gonna have you guys look this one up in the homework. All right, how to determine how fast and what voltage ranges, and what are some of the pitfalls that you may see in your amplifier if you're not if you don't specify your if you don't know the specification or how hot you're gonna run the amplifier. Okay. All right, so I'm going to show you guys a couple of more applications. These are called active filters. Okay, active filters is literally combining what you guys did in lab 3 with what you guys are doing in lab 4. You're basically doing a filter and then amplifying the signal at the same time. Okay, so you can build a high pass and low pass active filter. Okay, the way you would do this, okay, normally, right, with a sorry, is this a low pass? I'm trying to figure out amplifier. This is a, so high frequency gives you more current. I'm trying to remember if this is low pass or high pass. So this will be, well, let's derive it so we don't have to remember it, right? So why remember things when you can just do the math, right? Okay, so if you want an active filter, meaning you're going to plug a filtering circuit, that's what this capacitor is going to do, okay? As opposed to just a gain of RF over RN. Now the gain is going to depend on the frequency of the signal that comes in, okay? And I guess I also don't remember, I think this is probably, I'm not gonna guess what type of filter this is, okay? So once again, whenever you're dealing with a circuit, right, the gain, right, on an operational amplifier is basically whatever, if you're connected to the inverting input, right, it's the ratio of the feedback resistance to the input resistance, right? That's what an inverting amplifier does. But in this case, right, we don't have just resistance, we have a capacitor, right? So we generalize that to what? Impedance, right? So we generalize this idea to be the impedance of the feedback line and the input line, okay? And put a little negative sign in front of it so that we actually know that it's going to be an inverted input, okay? So the feedback loop only has a resistor on it, so therefore, of course, the impedance of a resistor is just the resistance. The input, right, has both a resistor and a capacitor on it, right, in series. When you add impedance in series, they just add normally, right? So that's what the gain of our active filter is going to be, okay? So now all we have to do is deal with this complex number, right? So this little complex number, what we're going to do is I'm going to, what did I do on here? Why is there just a R in RF here? I'm not sure what this is about. Maybe it got cut off. Okay, let's erase this, okay? So what I'm going to do is I'm just going to massage this equation until I get to something that's I can deal with, okay? So what I'm going to do, I'm going to factor out, oh, that's what I did. Okay, so I'm going to factor out RF and RN from the top and the bottom. So the top you get 1, the negative sign stays out here, right? If I factor out Rn, right, this becomes 1, right? So I need to have a Rn, oops, too many circles, Rn on the bottom, right? So this factors out, right? But then the denominator stays there, right? Okay, all right, and that's what this next line is, okay? Now what I do, okay, now, right, remember in a filter, right, omega RC, there's a special number, is 1 over RC, right? In this case, it's going to be Rn, because we're dealing with this Rn times C here, okay? So if we do that substitution, what you get is that the gain of this active filter is going to be Rf over Rn with the negative sign in front, multiplied by 1 over this complex number, 1 minus j omega Rc over omega, okay? Of course, to get to the gain, right, you have to take the complex conjugate, multiply by itself, and then square root the whole thing. If you did that, what you end up with is basically that Rf over Rn, which is going to be the gain of the circuit, okay, which is what you, this is the inverting amplifier gain, right? Inverting amplifier gain, right, which is what we did last week. Amplifier, spell it, okay? And this factor here, right, this is basically a high pass filter. Okay, if you go back and look up chapter 3, right, you will get exactly this factor here for a high pass filter. Don't think, right? Whoa, it crashed. Yay. All right. Okay, maybe next semester I'm gonna get a new laptop, new tablet. This is getting annoying. Filter. Right? Right. Does this make sense? How I just, didn't know anything about the circuit initially, and then just, went into, analyze it as if it's an inverting amplifier because you're plugging the input to the negative part, right? And then you just say, oh, instead of resistance, right, now you have capacitors, right? In order to deal with capacitors, you have to go to impedance, okay? Right? Okay. So this gives you some, let's say RF over RN is 10. We've got a 10 kilo ohm and a 1 kilo ohm, right? That'll give you a factor of gain of 10, right? If you are at, infinity as your input frequency. Okay. All right. Everyone believes me that this factor on the right is a high pass filter? Yeah. Right. Because as omega goes to 0, right, this basically goes to a big number. So 1 over a big number gives you 0. So it actually filters out low frequency. But when omega goes to infinity, right, this number basically becomes 1 over infinity squared, right? So this whole number just becomes 1. Okay. Okay. All right. And then that's what the output gain, the bot plot for this looks like, right? Once again, we're dealing with this 20 dB, 10 base log of the magnitude of the gain, right? So it reaches 1 times RF over RN, right? So if your RF over RN is 10, right, this will actually go up by a factor of 10, right? Well, actually it goes up by a factor of 1, but let's see, because of this stupid log scale thing. Okay. Okay. So these plots, don't think about this in terms of this chapter. These plots are from chapter 3, by the way. Okay, it does exactly the same behavior. It has exactly the same behavior, except you can multiply by this additional factor of RF over RN. Okay. For the low pass filter, the gain you're gonna get will be in your homework, but the answer is here. Okay, so you can write that down if you want to double check it. Okay. Okay. These numbers are, the equation is basically exactly the same, except omega RC is in the numerator, denominator instead of numerator. You just flip this factor in the back upside down. Okay, and that has the opposite effect, right? Now, when omega goes to infinity, right, this number gets really big. So a really big number, square root it. 1 over a really big number gives you 0, right? So big frequency goes to 0, right? When omega goes to 0, right, it gets very small, right, you get a factor of 1. Okay. Okay. And the way you set that up is that you put the capacitor in the feedback loop instead of the input. Okay, you just move the capacitor from one place to another. Okay. see these already. If you want to build a bandpass filter, am I deriving this? Yeah. Okay. Just as you did with the in lab 3 when you did a bandpass filter, right? You did a capacitor and an inductor, right? Now you don't even need the inductor anymore because, right, what you're doing, right, if you ignore this part, right, this is a high pass filter, right? I guess I can do this up here, right? If you just don't look at this part, right, this is a high pass filter, right? We just derived that, okay? If you don't look at this part, right, this is a low pass filter, right? So this is a combination of a high pass filter and a low pass filter, and when you do both, you get a band pass filter. Okay. Am I going to do this? Okay. So in this case, if you want to think about it physically, what's happening is that when you run this filter at this resonance, the energy is being transported between your input capacitor and your feedback resistor capacitor. Okay. Right? Because resistor doesn't really do anything, right? It just drains current, drains power, okay? So the energy is being transferred between these two guys, okay, and oscillating between them, okay? So to figure out the... Right. To figure out what is the... Remember when we did bandpass filter, we have this thing called Q factor, the one you guys are finished measuring, right? Already from last lab. Unlike what you can calculate from chapter 3, right now it's not as clear, where the current is going, where the energy is stored. Remember the Q factor was that it's the amount of energy stored divided by the power dissipated per cycle. Okay, it's a lot harder to quantify this because you just have two capacitors where you have charges just oscillating between them. But what you can do is that you can actually just physically derive this, because what's happening is that you have a low pass filter, which I'm going to draw like this, right? And then you have a high pass filter, right, which goes like this. Okay. Okay. The peak, the actual filter you're getting is this, right? Oops. Right. That's the bandpass, right? This is your bandpass. Write this. This is your low pass, and red is your high pass, right? You can easily derive this without dealing with this energy per dissipated per cycle thing, because you actually have equations to calculate these F3 dB point, right? This point is the high pass filter's F3 dB point, and this point here is the low pass filter's F3 dB point. Okay, so if you can calculate what those are, right, which is just 1 over 2 pi the RC values, right? That's what F3 dB is, right? Not a surprise, right? Right. That means the resonant frequency is actually the multiple of these, but then square rooted. Okay, you just have to get the right units again. Okay, to calculate what this resonant frequency is, right? You just multiply those two F3 dB point, and then you square root it, and that basically it's a way for in frequency space how you calculate averages. Okay, okay, the average between 10 gigahertz and 100 gigahertz is not whatever the additive average is you actually just multiply those two together and then square root it. Okay, all right. So now we have this. Remember, the other way to define the Q factor as opposed to energy stored over the energy dissipated is that you can actually just measure what the resonant frequency is and the bandwidth of your bandpass filter, right? Remember, the bandwidth is this. Let's do purple. Purple, right? This is the bandwidth. Well, you have this number. You have this number by calculating what the 1 over RC is, right? So you have what that number is, okay? So if you want to figure out what the Q factor for a active filter, right, that's the combination of low pass and high pass, you can actually really just calculate what the Q factor is, okay? All right. Oh yeah, and what happened is that since you're applying two filters as opposed to getting a maximum gain of RF over RN, you basically lose a factor of 2, okay? But you can just tweak that. Instead of using a 10 kilo ohm and a 1 kilo ohm, you use a 20 kilo ohm and a 1 kilo ohm, right? If you want a maximum gain of 10. All right. Yeah.
So for the delta F, would that be the same thing as applying the left and right 3 dB
Right.
points?
Because that's exactly what's happening here, right? You're doing the left 2 dB point and the right 3 dB point. But those are calculated with different RC values, right? Because they're combining both a low pass filter and a high pass filter. Okay?
And so at those points, the difference between the two would then be the bandwidth.
Right.
Okay.
Yeah. Yeah, you calculate the difference between them, right? You calculate what this number is, you calculate what this number is, take the difference, that's the bandwidth, right? And then you multiply the two numbers together, take the square root of it, and that'll give you the resonant frequency. Yeah. Yeah. It's actually kind of nice. You don't have to deal with thinking about, oh, where's the energy going, where is it dissipated, stuff like that. Because now you have 4 components, right? So some of the energy is dissipated through here, some of the energy is dissipated through here, and then, is the energy being stored in the feedback capacitor or the input capacitor, right? So this is much harder to analyze. I think you could do it, and you will get the same result, but it's going to be a lot more algebra. Okay. Another application. What time is it? So make sure. I'm gonna probably have to go like 5 minutes over, unfortunately, because I started late and there was a computer crash. Okay. Another application for operational amplifier is basically convert signals from cameras, even light or any type of light sensor, into electrical signal. Okay. And this is done through something called a photodiode. Okay. Um, in the back of your phone, right, you have a little camera here. These are basically just light sensors, right? Because it detects light from, all of you guys are reflecting light off the fluorescent tubes here, right? And your camera is able to capture that. And imagine each of these is basically going to be like 1 pixel on your camera, and your camera has like, I don't know, 12 million of them, right? Okay, and that's how it forms the image. Okay, so the first one here is a photodiode. I think a lot of you guys might have one of these in your kit. So I think I told you that if you look into your LED and it's black, that's a photodiode, not an LED, right? The way it works is that whenever light reaches, the depletion region in your PN junction, so basically they made it so that this part of your PN junction is exposed to light as opposed to covering up. When light reaches it, what happened is that it will liberate, basically promotes either an electron or a hole, right, to a higher energy level. So therefore, they are free to move away from this depletion region. Okay, and that's what the exposure and the wavelength of light is, either visible, right, and so that's typically about half a electron volts. And so this depletion region is designed so that with half an electron volt energy, it can escape this depletion region. Okay, and then what happens is that, well, when that happens, well, if you're an electron, right, now you're on this side, what will happen is that this electron will just flow around. Why is it going the other way? Okay. Oh, maybe, sorry. I think it's promoting it. Okay, so it's negative charge, of course. Sorry. It's negatively charged. It's just promoted to over here, and now this electron is allowed to flow through the circuit. Okay? So essentially what happens is that if you just connect the two legs of your photodiode together, there'll just be current constantly going around. Okay? You can think about this in terms of holes, okay? And let's, if you want to think about it that way, the holes can travel the other way, which is actually, the direction that positive current goes. Okay? So on your photodiode, the ones that looks like a LED, right? One of the legs will be slightly longer, okay? And I think the convention is still for current, positive current, to flow from the long leg to the short leg, okay? And then usually the symbol for this is like this, okay? And there's like a little sensor here that cuts next to it, okay? Interesting thing is that, right, a single photon, due to the photoelectric effect, creates one electron. You guys covered that in modern physics yet? Quantization of photons? Okay, not yet. Okay, so it's fine. One photon is a photon is a quanta, one little packet of light, and one of those little packets of light will give you one electron, which is sort of a neat little thing. And when you guys see the photoelectric effect, and you just tell Dr. Matari, I already know this. Okay, no, don't tell that. It's a very interesting experiment. Okay. So whatever number of photons that hits your detector, right, it'll give you one electron only. Okay. So typically, if you see normal light, okay, this will give you something on the order of 1 billion photons per second. Okay, so that seems like a lot of photons. Okay, but if you convert that to 10 to the 9 electron per second, what is the current? This is 10 to the 9 electrons per second gives you how much current? Right, right, because the charge of an electron, right, is 10 to the minus 19 coulomb, right? So the current is going to be that times 10 to the 9 electrons per second. You're going to get something on the order of, coulomb per second, 0.1 nano amps, right? Right? Nanoamps are a little bit hard to see. Okay? So what you typically do is you will actually amplify that signal. Okay? Before we move on to how to amplify that signal, we want to also show you that all these photodiodes has this thing called a response plot, meaning they are more sensitive to certain wavelengths of light. So for example, this a particular, I don't even know which model this is. You know, it's very sensitive to like 950 nanometers of light, but not as sensitive at like, 300 nanometers of light. Okay, so there's a wavelength dependency on how well your photodiode can actually detect things. Okay, let's not go through all of this. What I'm going to do is I'm going to show you guys how you can use operational amplifiers to basically convert that nanoamp of current, right, into a signal you can see on your oscilloscope. And these things are called transimpedance amplifier. Okay, so the reason it's called transimpedance amplifier is that trans means change something from one to the other, right? It's going to change current into a voltage. Okay, and it's a pretty simple circuit actually. You connect your little photodiode here, and then you have the current. Basically, typically you have positive charge going this way, right? You just have positive charge going to ground. You connect this to ground. These little triangles means ground, unfortunately. Okay, let me just change that quick. Okay, so on some circuit diagram you have these little triangles. They symbolize ground. Okay, and you put the photodiode, the the other end, into the inverting input, right? And then you put the non-inverting input to ground also, and you just have a little resistor and capacitor to it. Essentially what you need is just a resistor, okay? The capacitor is there to kind of remove the high frequency noise, okay? Okay. So how does this work? So let's just ignore the capacitor for now, okay? Let's just think about this in terms of the feedback resistor, okay? Right? So in this case, there's going to be current that's going down. I'm going to call that IPH for I photon, right? Okay, right? So as light hits my photodiode, it's going to create current that goes down, right? Well, this current cannot come from the negative input, right? Because there's no current coming in or out of these inputs. So that current has to go through the feedback loop. right? And since this is tied to, this is the negative input and the positive input is tied to ground, the voltage here has to be 0, right? Okay. So if you have current going from V out to through the RF to 0, that means V out minus 0, oops, minus 0, is going to be equal to whatever I times F, R is, right? I photon times RF. Okay, well, that means V out is equal to I photon times RF. Okay, okay. So that means whatever your voltage output on your operational amplifier is, it's going to be proportional to how much current that's being generated, i.e. how much light your sensor is detecting, right? Multiplied by this feedback resistor, okay? Whatever that number is, right? Okay. So if we make RF equals to maybe 1 mega ohm, right? And my I photon, right? What will I say? 10 to the minus 9 amps, right? Let's just pick a round number, right? V out is going to be how big? This is 10 to the 6. That's 10 to, so that's going to be 10 to the minus 3 volts, right? So that's about a millivolt. Okay, it's still a little bit too small, okay, for your oscilloscope to pick it up. But, you know, if you do this, you know, with a 10 meg ohm instead, then you would actually pick up 10 millivolts, okay? Okay. Yeah, let's talk about the capacitor part, right? And why is the capacitor useful? Okay. So when this happens, right, when your photon is getting into your photodiode, it's going to be like a random process, unfortunately. So sometimes it will get, you know, a billion photons. Sometimes it will get 10 billion, but then another time it will get 10 million or something. It just goes up and down. There's a lot of fluctuation, right, on how much current that's being received by your photodiode. Okay. So these are known as high frequency noise, okay? Meaning that it changes very quickly, right? So you don't want to look at that, right? Because all you care about is kind of like, you want to just kind of average over like maybe on the order of 0.1 seconds, how many photons you're seeing, right? So that's what this capacitor allows you to do, okay? So in this case, right, we have a capacitor and a resistor that are parallel to each other, okay? And we're not going to rederive it. Yeah, what's up? The dean wasn't there? Which dean? Ramirez? Is Christy there? No one is there? Okay. Do you mind chatting with him for?
No,
He's in his office.
He was just in Mark's office tonight.
Okay. Okay.
Should I contact to see where the dean
Yeah.
is?
Yeah. Can you email her?
Oh, sure.
Yeah. Thanks. Sorry, the visitor needs. Okay. Sorry. What was I talking about? Oh yeah. So these two devices are parallel to each other, right? And I'm not going to rederive it because it'll just take, you know, like 5 lines of algebra. But previously we have derived that if you have resistor and a capacitor parallel to each other, the impedance of that is going to go as 1 over square root of r squared, 1 over r squared plus omega squared times c squared. Okay? All right. And why is this useful? Right? Because as omega goes to infinity, remember you want this to be knocking out high frequency noise, right? Right? The impedance goes to, well, 1 over square root 1 over r squared. Well, when this goes to infinity, right, and you square it, it basically goes to 0, right? As omega goes to 0, right, then this second term basically goes to 0, 1 over r squared basically goes to 0, right? Then your impedance basically goes to r, right? So you get your regular impedance back, okay? Right? And that's why that little feedback resistor in there is very useful in order for you to knock out those high frequency noise that you'll see as the light, you know, that hits your photodiode changes at a very high rate. Let's not talk about integrating and differentiating circuit because we've already seen those. Those are very useful when you're doing Fourier transform though. Let's see. Yeah. Okay. So let's wrap up today. That way you guys have some time to finish your labs. Okay. And then I'm gonna